We're really excited for this opportunity here. So without further ado, welcome everyone to this session. This is the 2024 Turing Award winner speaker series. So we've had here at Georgia Tech, we've had 5 Turing Award winners. We now have our Nobel laureate in physics. We're really appreciative. Dr. Leggett is Nobel laureate in physics and is celebrated for his seminal contributions to the understanding of quantum liquids and superconductors, which profoundly influencing the field of condensed matter physics. So today he's going to be presenting the presentation, What Can We Do with a Quantum Liquid? And so without further ado, if everyone in the audience wants to give a warm virtual round of applause for Dr. Anthony here. Thank you so much, and we're excited.
Thank you.
Yeah.
Okay, so next slide, please.
Yep. Okay.
Okay, so I am a low temperature physicist. And if you were to show the temperature scale on the normal linear scale that we use in everyday life, then you'll see that the things I'm going to be talking about are all down here at the bottom end, below 100 degrees absolute. And some of the most interesting things that I study go on in this very tiny area, this tiny region right at the very bottom of the temperature scale, where I've said liquid helium boils.
Mm-hmm.
So you might think that low temperature physics is a very tiny part of physics in general, but that's really misleading. If I replot the temperature scale, the temperature on a logarithmic scale, in which every interval corresponds to a factor of 10, then things look quite different. Next slide, please.
Okay. Are you going to the next slide?
Yeah.
Okay.
Okay, that one we can skip. Yeah.
Skip it?
Yeah, okay, this one, right, fine. And now you see, in principle, I should be talking about all these things. In fact, I'll only have time to talk about a couple of them very briefly. But you see that according to this scale, low temperature physics has an enormous range. It goes through many powers of 10, many orders of magnitude compared to the ordinary room temperature interval. Anyway, I promised I'd talk to you about quantum liquids. So if I can have the next slide, I can just tell you what we need to make a quantum liquid. Yeah, good, thank you.
Yeah.
So we need 3 ingredients, basically, to make a quantum liquid. We need low temperature, which I'll discuss all these in more detail in a moment, but low temperature ensures us a high degree of order. We need quantum mechanics, which tells us that particles show wave-like behavior. And then finally, we need the system to be liquid. That is, that particles need to be able to change places. And that is actually a crucial ingredient in quantum liquids. It turns out if you put all these 3 ingredients together, then we get a quantum liquid. And those we can define as systems which show the effects of quantum mechanics plus the effects of indistinguishability of elementary particles. And I'll explain that in a minute. A particular subclass of quantum liquids is the so-called superfluids. These are quantum liquids which show macroscopic quantum behavior. Again, we'll see an example of that later.
Next slide.
Yeah, yes, please.
Okay.
Okay, so let's look at these 3 ingredients in a little more detail. As I said, in order to one advantage of going to low temperatures is that I increase the degree of order. And that's something you may perhaps be used to in certain examples. Suppose we have, say, a substance like, say, water. Then, crudely speaking, at high temperatures, the molecules of the water are just distributed at random, and moreover, they're moving around. If I go to low enough temperatures, of course, I freeze the water, get ice, and very crudely, in ice, we find that the molecules are arranged in a regular pattern, and moreover, they don't move very much around that pattern. So we've gone from a disordered situation here to a more ordered one here. Again, another example, with which some of you might be familiar, is a behavior of magnets, like say iron. At high temperatures, what we find is that the little atomic magnets which occur in iron are completely jumbled up and disordered. If we go below the so-called Curie temperature, which is actually quite high for iron, something like 1,000 degrees absolute, we find that the little magnets tend to all line up exactly in the same direction. Again, disorder at high temperatures, order at low temperatures. And finally, another well-known example is a disordered alloy, say copper and zinc. If red represents a copper atom and blue represents a zinc atom, then at high temperatures, you'll find that under certain conditions, the atoms just sit in random places relative to one another. Whereas at low temperatures, the alloy becomes ordered. The one zinc is always surrounded by several coppers and vice versa. So again, by going to low temperatures, we go from disorder to order. So that's ingredient number one. Next slide, please.
Okay.
Yeah. Next, you remember we also needed quantum mechanics. What quantum mechanics does for us in this connection is that it tells us that particles, under certain conditions, behave like waves. We can actually illustrate this with the following experiment. This is so-called Young-Slitz experiment. Suppose that we have a simple light bulb here. We've got to actually make sure that it's only emitting light of a certain wavelength and moreover in a rather well-defined direction, but let's suppose we're doing that. Then we can shine that light on a screen which has two slits in it, and then we can try to catch the transmitted light on a photographic plate, and under appropriate conditions, what we will see is a pattern of dark and light, light and dark lines here. That's a very well-known experiment. It's been known now for something like, I think, 200 years with light. But it turns out that if we're sufficiently careful, then with appropriate conditions, we can actually do this experiment, not just with light, but also with particles, like, say, electrons. This source be not a light bulb, but a source of electrons, and we again get the same kind of behavior, the same kind of so-called interference here. So that seems to show that qualitatively particles like electrons can behave like waves. And we can make this more quantitative. And this is what Louis de Broglie did in a famous relation he wrote down just about 100 years ago, I think now, which tells us that you take a property which is a wave-like property, namely the wavelength, and you relate that to a combination of particle-like properties, mass and velocity. Those are both particle properties. And there's an extra constant in that relation to get the dimensions right, and that is the so-called Planck's constant, 6 times 10 to the minus 34 joule seconds. Very tiny on an everyday scale, but nevertheless very, very crucially important when one comes to look at the properties of atoms and electrons and things like that. So yeah, so sometimes at least particles can behave like waves, but let's just try to examine that a little further. Next slide, please.
Yep.
Yes, it may be that despite the fact that the wave is really, in some sense, particle-like. Nevertheless, you don't see that. It may look perfectly innocent. And that really depends on the wavelength of the wave and the geometrical dimensions of whatever it's passing through or interacting with. So what we have here, this is a wave with wavelength lambda up here, and you see that it's incident on a slit in a screen. The width of the screen is A here. Suppose that first the wavelength is much less than the size of the aperture here. Then the wave will go straight on, and it will actually appear to be simulating a particle. And that's why, in fact, Newton could believe that light was actually a stream of particles. In a sense, he was right, but he was 300 years ahead of his time.
Mm.
But anyway, we normally tend to think in everyday life of light as a wave. When do you see the wave-like properties? Well, suppose that the situation is reversed, and the wavelength of the wave is now large compared to the dimensions of the aperture. In that case, you get the phenomena known as diffraction and interference. The wave does not simply go straight through; it rather gets spread out in a very systematic kind of way. Incidentally, there's a very simple everyday phenomenon, which at least partly is explained by this difference here. Consider the fact that you can hear around a door, but you can't see around a door. It's not the only feature involved, but crudely speaking, one reason for that is that in the case of sound, you're talking about a wave whose wavelength is about the same or a little bigger than the size of the door. So the sound doesn't need to get spread out. On the other hand, light has a wavelength which is very tiny compared to the size of the door. That just goes straight through. As I say, that's not the whole story, but it is at least part of it. Okay, so when can we actually attain this situation here? Well, according to de Broglie, the wavelength is related to the particle-like properties by this relation here, h over mv. And so to get lambda greater than the aperture, we need that v is less than or order h over mv. Now, for a typical gas in equilibrium, the mean square value of the velocity is the order of the thermal energy here. And the thermal energy is so-called Boltzmann's constant times the temperature. Boltzmann's constant is, again, a very small quantity on the everyday scale, has a magnitude of about 10 to the minus 23 joules per degree. So that means that what we need to see wave effects is that the temperature of the gas we're talking about, or whatever system we're talking about, is less than of order this quantity here. But the problem is, what shall we put in for A? Well, crudely speaking, if we're talking about a system containing many particles, then it seems sensible, at least for a first shot, to put A equal to, or the order of the distance between particles. And so in a gas or liquid or solid, we'll take the slit with A to go with the order of the interparticle spacing. That's a bit of a guess, but it turns out it does work out. So in order to get wave-like behavior, we need, well, for atoms, we need that the temperature is less than about 20 degrees K divided by the atomic number. Could you just push the slide up a bit so we can see the last line?
Yeah, let me see if I can. Oops. So it looks like it says, oops, sorry. Electrons show wave-like behavior for all T in liquid solid phase. Do we see this?
Yeah, well, okay, that's fine. If you just read it, if they can hear that. Yes, okay, we can, okay, then I think we can go on to the next slide.
Okay. Next slide. Okay. Do we see this?
No, I don't. I don't see
Okay.
anything. Oh, I see.
Maybe it
It's,
when I went out of the thing, maybe it let me just say.
yes, right now I can see you.
Yeah, sorry guys. Okay. Um,
Yeah, okay.
good.
Yeah, that's fine. Good. Fine. Okay, would you remember? So the condition for waves for particles or things we normally think about as particles, like say electrons or atoms, the conditions for them to behave like waves requires these rather low temperatures, at least for the atoms. As I said, for the electrons, you already have that condition the moment you have a liquid or a solid, so that's not a big bother. But for atoms, you do need low temperatures. However, that's not enough to get a quantum liquid. You remember we had three conditions necessary, and the third, which is actually crucial, is that the atoms or electrons or whatever we're talking about should be able to move around and in particular change places. Now, that isn't really relevant in the case of a gas. In the case of a gas, usually you have this condition, and you remember that this condition was the one which gives you no wave-like effects. So we don't even have really quantum mechanical effects in a gas under most conditions. Not all, but under most conditions. For a solid at low temperatures, things are a little more tricky. For solid at low temperatures, we do have the wavelengths greater than the typical interatomic dimensions. And so quantum mechanics does work. We do expect our particles to behave, at least in some ways, like waves. But in a solid, the atoms are usually stuck near their positions. They vibrate around their positions, but they don't change places. So finally, let's consider a liquid at low temperatures. In a liquid at low temperatures, we have all our conditions fulfilled. Lambda is greater than the distance between particles, and the atoms change places. And that will happen if we have a system which, for atoms at least, is less than, for which the temperature is less than about 20 degrees Kelvin and still remains liquid. Are there such beasts? Well, yes, there are. The main candidate in this region is the element helium. Helium does indeed remain liquid under its own vapor pressure, as far as we know, right down to zero temperature, certainly below this kind of temperature down here. And that's why there's been such an immense amount of work on liquid helium over the last 50 years or so. There's a second class of systems which I won't have time to talk about, which are the so-called ultra-cold atomic gases. Again, there you find all the conditions for a quantum liquid fulfilled. Helium has been the main candidate. Now, for electrons, as I've already mentioned, all liquid or solid metals work because, by definition, in a metal, the electrons are able to move around and change places. So basically, the class of quantum liquids consists of these two lines at the bottom, helium at low enough temperatures, and the electrons in liquids and solids. So what does this buy us? Next slide, please.
Next slide.
Okay. This is where the indistinguishability of elementary particles comes in. Because particles behave like waves, that means that it's impossible to tag them, to put, as it were, a mark to distinguish one elementary particle from another. Well, that doesn't matter, for example, in a solid, because in a solid, you can just basically tag the atom by the position it occupies, right? Well, what happens if you have a liquid and the atoms are moving around? Then you have the following situation. Suppose that we were to try to tag them. So let's imagine we start off with two atoms here and here, and we'll call this atom Bob and this one Fred. But now they're going to behave as waves and start basically diffusing all over the place. Suppose a little time has elapsed and we've now got this situation here. Is this one Bob and this one Fred, or vice versa? That is, did we have a situation like this, or a situation in which Bob, as it were, migrated over here and Fred migrated there, or did Bob rather do this and Fred do that? We
So
don't
it's
know.
like impossible. It's impossible to tag them.
Yeah.
And identify.
Yeah. But it is crucial, you see, for this property to be important, they must be able to change places. And incidentally, for anyone who's interested, the very, very neat illustration of that is the energy levels of the carbon molecule. You find that in the vibrational motion of a carbon molecule, when the atoms are just doing this, then the indistinguishability doesn't matter. In the rotational motion, when they're doing this, it matters extremely. Behavior is totally different. Anyway, I say we do need change places. Next slide, please.
Yep. Oh, did I do it? Yeah.
What this indistinguishability leads to is the notion of so-called quantum statistics. It's a quite subtle notion and took a long time to try to understand properly. We think, at least in some sense, we do understand it now. We can classify elementary particles, as electrons, protons, neutrons, and so forth, into two classes. One class has intrinsic rotational motion, intrinsic spin, equal to a half this quantity h bar, which is actually, apart from a factor, is just Planck's constant. So these have half integral spin in units of h bar. And these are particles like, say, electrons, protons, neutrons. And it turns out that the consequence of the indistinguishability, this is not at all obvious, it had been worked out over many years, but it turns out that the consequence of this this indistinguishability is that fermions can have at most one particle per allowed state. So if I plot the energy of possible states of, let us say, an electron in a simple metal along this axis here, I find that the number of particles occupying that state is basically at low temperatures is just equal to 1 up to the so-called Fermi energy, when it drops pretty rapidly to 0. And so at first sight, that's rather boring. The opposite class of elementary particles are those which we call bosons. They have spin 0, h bar, 2h bar, and so forth. Right now, the only stable, well, it's not really stable, but the only common, let's say, the only common elementary particle we know which falls in this class is the photon, the quantum of light. But it turns out that compound particles, there are also a lot of compound particles, which are bosons. And we'll see in a moment how that works. Bosons, as we've seen just now, fermions were very xenophobic. They will not tolerate more than one particle per state. Bosons are quite the opposite. They're extremely gregarious. And in fact, under certain conditions, they like to have a macroscopic number of particles, a finite fraction of all the particles in a single state. And that is the state which is known as Bose condensation, Bose-Einstein condensation, BEC. And that turns out, it basically is this phenomenon, which is the root of most of the properties of quantum liquids, which I and many others find so fascinating. Okay, let's go to the next slide, please.
Next slide.
Yeah, I think we can skip this one. It's a bit too
Skip this one.
technical. But yeah, right. This is good. Okay. Now, we've actually known about Bose condensation. We think we've known about it in the context of liquid helium for many years, way back to the 1940s, I guess. But in the mid-1990s, I think 1995, it turned out that one could also achieve Bose-Einstein condensation in a different system of bosons, namely atomic Bose gases, like so atomic rubidium of the right isotope and so on and so forth. And this is actually done not in, yeah, well, it's the year here.
95.
See it, you can read it, I think it's not 95, yeah. Okay. This was achieved by, as a matter of fact, by several groups in the latter half of 1995. And the journal Science always likes to select at the end of the year, for its last issue, it selects a molecule of the year. And usually this is some complicated biochemical molecule or something like that. But this time they designated as the molecule of the year the Bose condensate. And they illustrated the Bose condensate by this picture, which I think is a very nice one. It pictures the Bose condensate as like a platoon of soldiers who are all marching exactly in lockstep, all doing exactly the same thing at the same time. And you see they've also illustrated the fact that not all the atoms are necessarily in the Bose condensate. There are these guys which are different from one another, and they're all running about doing their own thing. But every atom which is in the condensate must be doing the same as every other atom there. That's, as it were, in some sense, the defining feature of a Bose condensate, and it applies not just under strictly thermal equilibrium conditions, but under quite non-equilibrium conditions in many circumstances. Okay, next slide, please.
Next slide.
Yeah, I think we can skip this one. This is I'm having to skip several slides because this is the longer version of the talk. I was intending originally to use the shorter version, so now we have to skip a few. Yes, this one can also skip.
Skip this one too.
Yeah, we didn't skip. Well, okay, just very, very briefly, this is very crudely the pattern you see, and if you look for the density of a gas of ultra cold Bose atoms in an appropriate geometry. You see the condensate is all concentrated in a very small region around here. The normal component, that is the non-condensed atoms, they're basically spread over a much larger region. So this is one advantage of the development of Bose condensates of ultra-cold atomic gases was that in the case of helium, it's very, very difficult to see directly that Bose condensation has occurred. And you had to look for very indirect evidence of this, like, say, the ability to flow through narrow cracks and so on and so forth. In the case of the atomic gases, you can pretty much see Bose condensation occurring with the naked eye. However, I would not recommend you to try this because these things are usually stabilized by lasers, and you don't want to put your eye in the path of the laser if you help it. But anyway, in principle, you could see this with the naked eye. Okay, next slide, please.
Next slide.
Okay, yeah, again, this is too technical. We want to skip this one.
Skip.
Yeah, okay. One very, very spectacular manifestation of quantum liquid behavior, and it's probably the only one I'm going to have time to talk about in any detail, is superconductivity. If you asked me to demonstrate superconductivity to you in a simple high school or university lab, what I would probably do is to try to construct a circuit like this. I make it mostly of the black material, let's say copper. It's not a superconductor, or it's not known to be. And then I would have a part of the circuit here, the blue bit, which is made of, let's say, aluminum. And I would drive a current, a known current through this circuit, and measure the voltage across the blue bit, the aluminum. By definition, the resistance of the aluminum is then the ratio of the voltage to the current. And at room temperature, this is just some value of some number of milliohms or microohms, centimeters or whatever, nothing special. If I now lower the temperature, this does in fact decrease. And it was originally thought 100 years ago that, more than 100 years ago now actually, that it might go to zero as the temperature went to zero. But what was very unexpected and was found by Camerlingionis in Leiden in, I guess, 1911, was that when he did this with a particular particular metal, namely mercury, the resistance did indeed go down smoothly, but then at some temperature, mercury is about 3 degrees, I think, it just drops precipitously to zero. Below that temperature, apparently there is no voltage across the aluminum and mercury, and therefore, by the usual definition, the resistance is zero. And that's what he called superconducting, and has been called ever since. So, how does the property of Bose condensation that I talked about, how's that related to this experimental behavior? Before I go to that, let me just briefly show you a graph of the highest temperature, so-called transition temperature, at which superconductivity is believed to occur. Next slide, please.
Yep.
Yeah, okay. So as I say, way back in 1911, Camerlingionis discovered superconductivity in mercury at about 3 or 4 degrees. Over the next, how many? 70 years or so, the superconducting transition temperature gradually crept up as more and more materials were discovered which became superconductors, until in the summer of 1986, the highest transition temperature known was somewhere around 25 degrees in a complicated alloy. And then things started getting really exciting. In the latter half of 1986, people discovered superconductivity in various copper oxide compounds at temperatures which kept increasing and increasing, in fact, until nowadays in these materials, it occurs around 125, possibly 150 K. And that was spectacular enough. These are the so-called high temperature superconductors. There's been a huge amount of research on them over the last 40, 50 years. 40 years, yes. But then something quite unexpected happened in around 2014. Namely, again, superconductivity was discovered at an amazingly high temperature, almost room temperature, but problem at a pressure of millions and millions of atmospheres. This has been a very active and controversial field over the last 10 years. Some people, most people believe that this is for real, that these they're actually mostly metallic sulfide compounds, that they really are superconducting under these extremely high pressures at very close to room temperature. But there have been a number of cases where these claims have had to be retracted. And some people, there is a small group of people who believe the whole thing is in fact just a complete fiction. And these high these ultra room temperature superconductors really don't exist, or at least have not been found. Anyway, that's where superconductivity occurs. How does this relate to what I was telling you about quantum liquids? Next slide, please.
Yep.
Yeah. Well, we already saw, and I'm just recapitulating here really, we saw that elementary particles fall into two classes. There are the fermions, which have half-mod integral spin, and the bosons, which have integral spin. And at low temperatures, they behave in these totally different ways. Remember, the fermions are very xenophobic. They don't like more than, well, they will not tolerate having more than one electron per state. The bosons are extremely gregarious. They love having a lot of particles in the same state. Now, if you're trying to relate this to superconductivity, it's a problem, because we believe that the prime actors in superconductivity are the electrons in metals. And the electrons in metals have spin 1/2, so they're fermions. So they should behave, apparently, in this very boring way. And indeed, in some metals, like, say, copper, they do behave in this very boring way. But it turns out that a compound object consisting of an even number of fermions can actually only have integral spin, 0, 1, 2, etc. In other words, it behaves like a boson. For example, if I just think about the helium-4 atom, then the helium-4 atom has 2 protons, 2 neutrons, 2 electrons. That's 6 fermions in total. So that should behave as a boson and should be able to undergo Bose condensation. And indeed, we believe that is what happens when liquid helium-4 becomes superfluid, as we've known for more than half a century now. Next slide, please.
Yep.
So crudely speaking, the idea is that not single electrons, but pairs of electrons can get together and form effectively bosons, and then undergo a sort of Bose condensation. Now, you might think that the picture is something like this, that 2 electrons form a tightly bound, what we might call a dielectronic molecule, and that these molecules are then rather well separated from one another. That's a possible picture, and some people believe that in some of the high-temperature superconductors, that could even be something like the right picture. But most people don't, and certainly most people don't believe this about the traditional superconductors like aluminum. Rather, they believe that the picture is more like this here. You have 2 electrons here, which are in some sense forming a pair. They're getting together and correlating their motion. But between them, there are any number of other electrons which are all trying to form their own pairs. People sometimes compare this to a form of modern dance in which I and my partner may be extremely correlated in our motions, but we are at opposite ends of the room. And between us, there are any number of other couples trying to form their own pairs. So it's a very, very collective phenomenon. But what is very interesting is that in the simplest theory of superconductivity, which is actually developed by my colleagues Bardeen, Cooper, and Schrieffer here in Illinois way back in the late 50s, in the simplest theory, these so-called Cooper pairs, pairs of electrons like this, the moment they're formed, they must automatically undergo Bose condensation. And that means, as we've seen previously, that they must all do exactly the same thing at the same time. And remember, that's true not just of an equilibrium situation, it's also true under many non-equilibrium conditions. So now let's just try to get a very simple and intuitive idea of why this might lead to the phenomenon of superconductivity, or to be more accurate, to one of the main phenomena of superconductivity, because in fact, superconductivity is not a single phenomenon, it's several which usually go together. But let's just take the phenomenon of zero resistance and concentrate on that. Okay, so I usually illustrate this. This is going to, I think, think will have to be my last slide. But I normally illustrate this with an analogy, which involves a forest. Now, this is a naturally occurring forest, so the trees are not in a regular array, they just occur more or less at random. And now I imagine that I take a bunch of school children and send them off running into the forest. But I give them no particular instructions or directions. Well, initially, they'll all be running exactly together, but sooner or later, one kid is going to come up against a tree, and she has no special instructions as to what to do, so she just swerves to avoid the tree. And because she has no special instructions, she'll just keep running on in the new direction. And after a fairly short time, all the kids will be running in totally random directions, and on average will be no particular motion, no average motion. That's, roughly speaking, the analogy of what happens to single electrons in an ordinary metal at, say, room temperature. Very crudely, you start off all the electrons with a particular voltage pulse there, and they're all traveling together. But sooner or later, one electron runs up, not against a tree, of course, but against a chemical impurity, let us say, and it will swerve off in a random direction. And as it were, has no particular instructions as to what to do, so it'll just keep moving in the new direction. And again, after actually a few microseconds in most cases, the electrons will all be running in random directions. That'll give you no electric current. The current has just died down. The current which was produced by the original voltage pulse just died down to zero. And that's what happens if I just do this in a copper wire, so no particular mystery. Well, now let's imagine a different analogy. Let's take our forest again, and let's imagine that we have not a group of school kids, but a platoon of rather well-drilled soldiers. And these soldiers have the instruction that, come what may, as far as possible, they've got to try to keep in step. They've got to try to all be doing the same things at the same time. Well, again, they all start off moving together. And now, actually, we shouldn't be talking about single electrons. We should talk about Cooper pairs. These pairs forming here. Okay. So it's the Cooper pairs, not single electrons now, which have this instruction. So they'll go off moving together originally. Eventually, one pair, or rather one electron of the pair, will run up. Sorry, I've got off my analogy, haven't I? Because I started off with a platoon of soldiers. So let's actually stick with that platoon of soldiers for a moment, shall we? They'll start off marching in step. A soldier comes up against a tree. Again, he has to swerve to avoid it. But the crucial difference is that he now has the instruction that as far as possible, he's got to get back in step with his comrades. So he gets back into step, goes on marching in the same direction. And this happens many times, that even after many collisions with trees, as it were, the platoon is still marching as one, straightforward. And that's the analog of the Cooper pairs in a superconductor. Again, they start off moving as one. Eventually, Cooper pair, or one electron of the pair, bumps up against a chemical impurity. It gets perhaps momentarily scattered, but it knows that it has to do exactly the same thing as its fellow Cooper pairs. It gets back in step again. And even after a long time, the Cooper pairs are all doing exactly the same thing, moving in exactly the same direction. That still gives you a large current. And so that's how the current in a superconducting ring can continue to flow for as long as you care to look at it. And just as an amusing historical note, the first public demonstration of this was made by Cameron Yonis's team in the I think the early 20s, when both not only superconductivity but also air travel was to some extent in its infancy. And what they did, so remember that Castiglionis was sitting there enlightened, but what he did was to take a dewar of helium and dunk a superconducting loop in it. He then, by varying the magnetic field, he created a circulating current in the ring, which is superconducting. And he then got one of his assistants to take the flask, get her on an aeroplane, fly across the channel, and exhibit this at the Royal Society in London. And that, as I say, I think was the first public demonstration of superconductivity. Needless to say, nowadays we can do much better. And one of the ways in which we've been able to do much better is to put a lower limit on the time necessary for the superconducting current to decay. And under most conditions, it turns out that this is many 10 times the age of the estimated age of the universe. So this really is a very, very metastable phenomenon. Anyway, that I guess is, yes, that's really about what I have time for. But there are many other phenomena associated with quantum liquids, with say liquid helium or superconductors or a few other systems, which sometimes already all go back to this phenomenon of Bose condensation. The idea that you have either a single elementary particle or perhaps a pair of elementary particles, which all have to be doing exactly the same thing at the same time. And that's really, to me, what's, I think, one of the most fascinating things about quantum liquids and why I continue to do research in that area. Thank you.
Absolutely. Okay, just 1 second here while I get back to my little script. Okay, so thank you so much, Professor, for your extremely insightful presentation. Can I get a virtual round of applause from the audience members for this? So thank you so much for taking your valuable time to educate us students. I'll be following up with you shortly to inquire where we can send you Godiva chocolates as a thank you appreciation. And we want to extend our deep appreciation of your time and your willingness to speak with us. Thanks as well to everyone in the audience for your attendance. And we really appreciate this speaker series that we had this semester. This is our final event, and it's been an absolute pleasure. And we're just really appreciative for everyone's attendance.
Thank you.
Okay, so I'll see everyone, and Professor, I'll be following up with you shortly to inquire where you can send some chocolates.
Thank you very much. It'll be very
Okay.
welcome.
Thank you so much, Professor.
Okay. Bye-bye.
Okay. Bye, everyone.
Bye.